Hello everybody, and welcome to our panel debate today entitled Perspectives on Layer 1 Offload in the Virtualized RAN. I'm Caroline Gabriel. I'm the co-founder and research director at Rethink Technology Research, which is an analyst firm focused on the mobile networking industry based out of London. I'm delighted to be the moderator for this session today. We'll be talking about what I think is one of the most critical and important issues that's facing operators and OEMs as they embark on a journey towards the virtualization of the 5G network. We've got three very expert and interesting panelists. Tejas Bhatt, who's the VP and CTO of wireless platforms at Marvell, Alan Gatherer, who's the CTO at Cirrus 360, and Steve Papa, who's co-founder, chairman and CEO of Parallel Wireless. They'll tell you more about themselves as we go through the conversation, I'm sure. A few opening remarks. As I say, I think the discussion we're having today is extremely timely. Virtualized RAN is clearly in its infancy, but most 5G operators are just at the stage of starting to make serious evaluations and plans of how they will approach this architecture, even if that's in a few years' time or even more away. Only if the industry can address their concerns quickly will they have the confidence to proceed at scale. So the issue of how layer 1 processing is handled has always been a critical one for the RAN vendors. It's nothing new. And with every generation, the challenges have got bigger as new performance expectations, new antenna technologies, new spectrum bands have been introduced. But in a closed RAN ecosystem, that was a problem for a few vendors and their partners. In a virtualized RAN environment, there are many additional questions over the location of the layer 1 processing. How's it split between the radio unit and the distributed unit, for instance? And there are two strategic objectives among operators that may not always support one another. One is to open up the ecosystem in vRAN and even more in openRAN. And the other is to achieve the flexibilities of the cloud environment while also being able to meet the unprecedented performance demands of 5G use cases. At Rethink, we carry out regular surveys of over 100 operators, as well as OEMs and other ecosystem players, about their objectives and their challenges in vRAN. And as they evaluate their options, they're naturally raising some key areas of concern or uncertainty. And the one that regularly tops the list of challenges is whether they can deploy significant numbers of layer 1 and 2 processes in the cloud without suffering trade-offs in performance. They'd be confident of this in 4G, but they're conscious that their business models for 5G rely on being able to support extremely demanding levels of performance enabled by technologies like massive MIMO with beamforming. So the solution for supporting offload and acceleration at layer 1 in order to reach those targets and without additional cost or power consumption is one of the most critical elements of operators' consideration of their vRAN strategies and their timescales to deploy. And I will ask Tejas, Alan, and Steve perhaps just briefly to introduce themselves, and then we'll open up the discussion. Tejas.
Hello, my name is Tejas Bhatt. I'm running the wireless platform architecture team at here in Marvell in Infrastructure Processor Business Unit. I'm VP and CTO for wireless platform.
Alan.
Hi, I'm Alan Gatherer. I'm a CTO at a relatively new company called Cirrus 360. Our focus is on tools and automation for the development of specifically layers 1, 2, and 3 within openRAN.
And Steve.
Hi, I'm Steve Papa. I'm with Parallel Wireless, where we're developing oRAN software that spans from 2G, 3G, 4G, and 5G. So through layer 1, 2, and 3.
I think my first question is quite a foundational one. Do you see a fundamental difference between 4G, 5G layer 1 processing between an integrated base station unit and an L1 offload card in a virtualized RAN configuration?
Fundamentally, if you see in 4G, 5G L1 processing, the overall processing requirement are governed by essentially three different aspects, I would say. Interface, the features of their interface, the algorithms that you want to implement, and then of course the deployment architecture that you're choosing. So as a whole, 4G, 5G processing requirement, if you see from the air interface features or algorithmic point of view, I mean, if both integrated base station and virtualized RAN are actually targeting similar features, they would probably have similar requirements in general. However, virtualized RAN most often will be implemented with what's called now 3GPP functional splits and as standardized by oRAN and split 7.2. and some functionality like lower L1 would move to the antenna or closer to the antenna in the radio unit. In this specific case, the frontal interface would be packetized, and this would bring a newer challenges at the layer 1. Now, base station always had to do packet processing, but now it's inside the layer 1 where you have to now do a packet processing. oRAN will also bring challenges of compression, decompression. When you implement massive, this kind of architecture will also enable a more cost-effective front haul for massive MIMO. So there will be additional challenges in how those algorithms would be implemented. While the algorithms by itself will not be changed between, say, an integrated base station as well as virtualized RAN, some of these features with the oRAN packetized front haul might be more simpler or more straightforward to implement. In general, additionally, L1 would also require some significant algorithmic processing and real-time processing requirement. Both of these would require a heterogeneous compute environment in virtualized RAN. What it means for virtualized RAN in general is to meet the requirement for layer 1, especially the hard real-time and the algorithmic processing, there needs to be a smart offload requirements at the virtualized RAN processing to meet the KPIs of real-time processing, of network performance, of radio performance. So in that sense, while at high level, the features and the processing requirements might be fairly similar, virtualized RAN does bring in a new set of challenges in terms of deployment architecture and what needs to be implemented.
Thank you. Steve, perhaps I'll go to you now. Obviously, you're developing software, so it's very critical that that software is able to run optimally on the platforms. And I know I've heard you speak in other contexts about the importance of investment into these semiconductor architectures. So what's your view on what really is the difference in what we are looking at now compared to the traditional platforms?
Well, I would start out with the traditional baseband SoC was sort of a chip designed at the beginning of a G, and that was tried to be leveraged throughout the journey of that G as long as possible, okay? As we've gotten a more rapid increase on the demands of the operator, more carriers to light up, more spectrum, more sites, more nodes, I mean, more layers of MIMO, there's just more math being done. And it's increasing. It's not going to slow down. Okay. We can't afford to wait, 5 to 8 years to get the Moore's Law dividend to do more compute more cost effectively. Okay. So what we're looking at is when we develop software, we can ride the Moore's Law journey as fast and as agile as possible. Okay. As every new year, there's a new ARM core, or there's something else new. How does that latest silicon play a role for us to be more competitive? Because we can't sit back and just wait while there are very aggressive competitors out there trying to take advantage of the latest silicon. Okay, so that's number one. Number two is the footprint of RAN software is quite big, especially when you start thinking about, even for just 1G like 5G, what's a small cell that does 4x4 MIMO versus a macro cell that does 8x8 versus massive MIMO. Now add in 4G, because you're doing carrier aggregation with that, and you want it to run on some of the same compute resources. And often for much of the world, there's going to be a 2G or 3G in the mix as well, because they don't want different baseband units at a cell site. You need software agility across these architectures. Okay, so in a sense, getting the complete offering, making across the feature set you need, and then as Moore's Law evolves, you're trying to take for the highest volume segments and do as much cost and energy optimization as possible, right? That's kind of the journey oRAN or virtual RAN has to go through over the next few years.
If you're a telecom data center provider, what are the main considerations that you need to take into account when you're provisioning for these vRAN offload requirements? And this seems a very different challenge from what telco data centers have had to think about before.
I would say on one hand, virtualized RAN may help in bringing the best practices that's already being developed for cloud and containerized software provisioning, orchestration, management, and software upgrade, right? I mean, it is going to improve in terms of how the RAN software being developed, deployed, and managed throughout the life cycle. And this technology and automation would help both the cloud or even a far edge cloud applications and deployment of the RAN network. However, there are several challenges that we see. One is in the L1 processing, as we have discussed before. It's a hard real-time processing. It does require a very low latency processing requirement in 5G. And if it is not taken care of, it can adversely impact the network capacity, system performance, and can reduce the 5G gains or applications applicability of the 5G that's being discussed in the industry. Also, we believe that GPP by itself in L1 workload is not sufficient. It will either lead to an application not being supported, or it could be a pretty cost prohibitive in terms of both capital and operating expenditure. So to meet this requirement, an L1 processing needs to be looked into more and from the heterogeneous compute offload point of view. And also it would require to meet some of the 5G workload, not just the layer 1, but even layer 2, layer 3, some of the bare metal processing would come into the picture as well, meaning you cannot actually have the baggage of virtual machines and guest operating system and so on and so forth, but it needs to be a lean containerized implementation that needs to be considered. Now, the good thing is this is something cloud providers are already considering for various other applications as well. So that's a good news. Now, I would say also while functional offload may help achieve some of the real-time performance and reduce the need for the compute in general. This needs to be looked into more holistically of how the offloading is being done. If you don't choose your offload workload wisely, you may end up having a problem of bandwidth where actually the PC, even the state-of-the-art bandwidth to move the data from CPU to offload and from offload back to the CPU will not be sufficient. So that needs to be taken care of. I think another key balancing act also needs to be the flexibility that is being provided by software versus the requirement of heterogeneous compute need, where certain thing needs to be hardware offloaded, certain thing may require a specific workload acceleration, just like machine learning would require a specific type of acceleration. I think L1 does provide that kind of challenges. So this needs to be looked overall in the scope of that. And I think a standardization of a workload profile and how those workload will be accessed by the software would go a long way here.
Yeah, I mean, I think, the data center guys have done an amazing job over the years, and I think we just need to pay attention to them, to be honest with you. There's a lot of stuff going on in data centers, a lot of learning going on in data centers in terms of tuning of the hardware itself to get the maximum benefit. Guys like Google now are telling their equipment suppliers exactly how much cache they need, for instance, right? Because they've got all of this data analytics. So I think we can go back to Hennessy and Patterson's Turing paper and the Turing Award paper, and just look at what those guys said and pay attention to it, which is really kind of a summary of where data center was and is going. And what they said was, they said, first thing they said was, we need domain specific architecture. So that plays to what Tejas just said, that the data centers realized, the data center guys realized they couldn't just go simply with kind of general purpose processors anymore, just GPPs. They realized that they needed some form of acceleration. Now, of course, we have the advantage of really already being there in our space. But the other thing that Hennessy and Patterson said is, and this is something we need to pay careful attention to, and it comes back to this code base issue and the automation issue, is we need domain-specific architectures, but we also need domain-specific languages.
Something I'd also like to come back to Tejas now to kick us off on another question that has become recently, I think, very topical, which is inline versus look-aside L1 offload. I think perhaps even in our sector, this was a fairly obscure topic of discussion until quite recently, but some of the big names of our industry have sort of made it into something of very public debate, that even operators are getting somewhat interested in it now. So I'm interested in the thoughts of the panel on what are the pros and cons of inline versus look-aside, and do you have to choose one or the other, or is there a coexistence that you can have so you get the best out of both?
Yes, so I think maybe just discussing as just in the style of inline versus look-aside is probably missing the point. I think at the end, virtualized RAN is driving a specific new architecture, a speed of deployment, speed of new feature introduction. And also it needs to be something that is feasible, economically viable. In that sense, I think what is going to govern this overall debate and what's the right boundary between inline, look-aside offload, what is done in inline, what is done as a look-aside, or what features and what deployment uses one versus other. I think that would evolve as we move forward, and as the technologies matures, both in the 5G standardization as well as the hardware technologies. So I think as of now, in general, there are certain criteria that's sort of given from the theoretical point of view. You may want to choose the right offload so that to make the flexibility that's offered by the vRAN from the software point of view stick, but then also make sure that the tight feature requirements from the layer 1 software in terms of latency, in terms of performance is also met. I think in that sense, inline offload does offer certain advantages with respect to reducing the overall bandwidth requirement in the data center. I mean, PCIe, if you think about it, as of now, still most of the data centers and most of the servers are still at Gen 3. Of course, now Gen 5 has been standardized, but it will take a while before the deployment of Gen 5 and availability of Gen 5 in the data center is available. So inline may help in that context. It does improve overall system processing latency by terminating oRAN front haul, packet processing inside, and take it away. I mean, if you see even now, some of this packet processing is done in the NIC, in the traditional Ethernet NIC, right? So I mean, an oRAN front haul is just another packet processing requirement. So that's another aspect that I mean, where it will improve the overall performance. It also will improve the overall capacity and the latency by having a heterogeneous compute. On the other hand, look-aside offload does provide a flexibility, but it could increase the overall OPEX and CAPEX because I mean you are doing more in the general purpose CPU. I think in general that there is a smart processing where you can actually look the overall processing with respect to data channel and the control channel, or user plane and control plane, and then you can actually say parts where we don't actually need to have a lot of flexibility versus a control plane in control some of the control applications and channel where you probably need a lot more software flexibility. So you can actually choose a different type of fleet.
Alan, Steve, any further thoughts about this particular debate that's going on in this area at the minute?
Well, if I would say, first of all, they coexist. Inline, right, and look aside, it's largely definitional in terms of which segments, how you deal with it in your software. Okay, there is always a cost to moving bits, right? We think of it in terms of energy, right? We think about joules per bit to move these things around, okay? And you're trading that off against what computational resources will be more cost effective, given you're incurring that tax to get it over there. These things will be constantly moving, right? Each different silicon device that one might incorporate into a system that's complementing other silicon devices might bring different trade-offs, okay? Also, as you load the systems, and you might end up with greater latency sensitivity that you might find doing an offload allows you to get more utilization from the rest of the resources, right? So there's a lot of different trade-offs that come in. The two coexist. Like I said, the first order of business for oRAN is to get the full thing working well. And then for the volume use cases, it's optimizing it, for both cost and energy as effectively as possible along the lines of what Tejas had spoken about.
I think that's a great note to finish on. I think that feeds into a lot of the broader thinking and messages around vRAN and Open RAN. So I would just like to wrap up by thanking Tejas, Steve and Alan very much for all your really insightful comments. Thank you.